Hey everyone, my name is Andre. I'm the founder of Ecliptor, where we do document processing at scale for a variety of use cases, predominantly in health tech and insurance tech customers. Today I'm presenting SynthForm towards a DLA-free end-to-end form understanding model, along with uh, my friend Eagle, who's unfortunately not here today. This is presented at WACV 2026 in Tucson, and really excited to be here to present our work. Cool. So I'll just go through a quick motivation setup, kind of how we assembled the data set, some of the architecture and training for what we did around SynthForm, and then just go through the evaluation results and discuss some limitations at the end. Cool. So I'll take a step back. I think I know there's people from around the world here, but I wanted to kind of highlight in North America one of the big challenges that underpin our workflows in healthcare system. Typically, when you go to a provider in the United States or Canada, typically what ends up happening is that the doctor will take your information, and then if you want to have to do some other tests, for example, an ultrasound, an X-ray, or what may have you, they will actually physically fax a form through copper wires across, these copper wires to this other to this other clinic, where then you have to go acquire the actual form on their side. And you can imagine that faxing introduces a lot of artifacts and a lot of different variations in the digitization of that form. And so this is a really big challenge that one of our customers was facing, especially with healthcare form intakes. So in order to kind of address this, this was kind of like the opportunity for us to take a look at the different variations in document processing that we can kind of help them with. Um, so these forms are a really critical part of these workflows, but the field level accuracy is really difficult, right? So birth dates are, an important criteria here. SSNs are really important, but they don't actually, if there's an error in SSN, you can imagine it causes a headache with insurance downstream. And so even just slight errors in these processes cause huge downstream errors. So having really high quality interpretability from the forms is really important. And so these forms they don't arrive as these clean PDFs, as I mentioned. And so the one note that we had for our customers that like, hey, we are actually there's a ton of these OCR pipelines online, right? Azure Document Intelligence, AWS Tesseract, Google Document Intelligence, all of these products already exist. But why is there needing a new kind of product to solve this? Well, they're all trained on really clean data sets, right? They're trained on things from archive where you have a PDF representation, but the faxing produces these artifacts that actually constitute a distributional shift in the inputs, which is something that these models are not trained for, meaning that the results from the models are actually extremely poor. And this is a huge bottleneck and huge gap that we found in the industry. So the current kind of state of the art in the data set system and the dataset ecosystem here for form understanding is pretty small. Typically when we talk about the number of tokens that LLMs and VLMs consume, they're in the order of billions and trillions of tokens. But for form-specific data that we're looking at, it's very small. And on top of that, there's no perturbed scan data set, right? There's none of these data sets that actually look at scans and faxes for our customers. On top of all of this, the real world forms are all locked behind these HIPAA, PII considerations, meaning that researchers and evaluators can actually appropriately look at these data sets. We mentioned this earlier, but basically the state-of-the-art VLMs are all really brittle to the real world, right? They don't actually benchmark against these perturbed scans, which is a really big training gap. Um, on top of that, a lot of the big challenges that we saw were number one, the VLMs, they failed because of vision tokens. They're actually like decompressed representations, and a bunch of these errors accumulate upstream as well. And so basically, in order to get through all of these problems, there has to be kind of a new paradigm for us to merge and a new data set that has to be collected. So in order to like motivate that's kind of the motivation here. Yeah, to give you kind of our core contributions, the first thing is we contribute is a small data set where we are able to fine tune our model. And so this is the data set that basically has 3,500 samples across six very important domains: insurance, healthcare, a few others. And basically, we synthetically perturb the input faxes and scans in order to actually generate mimicking the real world faxes and scans that we wanted to look at. The second contribution that we have is a family of fine-tuned VLMs for form understanding. Typically, we have 2, 4, and 8B variants where we use a full parameter SF key, and all of the model checkpoints and training code are all publicly accessible. Cool. So let's dive into the form data set that we presented. So there's four main steps in our pipeline. We acquired around 4,000 forms from just manual and scraped domains. What we do here is that we use GPT-5 high reasoning in order to generate the actual HTML structure. And from HTML, then we're able to generate Markdown. And then Markdown is then we're able to then take the input raw HTML and have the SFT pair from that with the synthetic perturbation. So a real question is like, okay, why do we need HTML as this intermediate representation? Well, HTML is obviously it aligns heavily with the LLM pre-training mix, so it has an output distribution that works well. But the more important thing is that it's renderable in a browser. So we can have the visual fidelity between the input raw form and the actual HTML that's being generated, and we can enable visual clarity on whether or not this representation makes sense. And functionally, this is a deterministic conversion from HTML to Markdown, which allows benchmarking to be done easier downstream. This is done in Olomo and a few other papers, which allows us to kind of give us like a Markdown representation. Makes a ton of sense here. Okay, so how did we actually acquire these forms? So there's manual collection in some of the low resource domains, like in dental, healthcare, and insurance. And there's only a few hundred which I manually collected myself, and I had to deduplicate and review that these forms actually made sense. Then we had some public archives, the CRA, the Canadian Revenue Agency, some immigration forms, and the SEC financial documents. And then in both these cases, we take all these forms, we drop the samples that are like really pixelated, unreadable, and finally we have 3,500 samples or 3,417 samples after the filtering itself. Okay, so now the question is like, okay, we have this data set, great. Uh, we should use some process in order to generate the HTML. So what we ended up doing was few shot prompting GPT-5. And what the reason why we do that is because GPT-5 high reasoning uses a agentic high reasoning mode where it self-critiques the image, it crops, it zooms, and it basically inspects the generation of the HTML at the same time as it's trying to generate the HTML, meaning that it basically goes through this loop where it has this near perfect pixel perfect HTML representation that mimics the input image. And this is really critical because imagine a lot of tables, a lot of these different forms have a bunch of different variations, and getting a really high quality result for the input data set is really important. But of course, this comes to the cost of being really computationally and monetarily expensive. So GPT-5 high reasoning, I think for our entire data set, it took us, I think it was like $3,000 or $4,000. And the actual time it took was around like 6 or 7 minutes per form. So it both on the time and the representation, it was really expensive. Uh, so in a task that we have, I want to take a step back. So the GPT-5 instant intermediate reasoning, it could do well, but it had really terrible results at the bottom. So why does this happen? Well, HTML form generation is actually this like long horizon structured output task, right? So there's like you can imagine when you look at an HTML page, there's like actually the top and the bottom of the divs are like a nested div structure, right? But when it's outputting the top div, it may forget to by the end, it might not output the bottom div correctly, that kind of stuff. So there's a bunch of like exposure bias that accumulates in autoregressive decoding. And so the long chain of thought allows us to have the structural fidelity as it self-critiques. That's an important reasoning why we use GPT-5 high reasoning. And the cost is quite expensive, but as we show later on, generating the data set with high fidelity is really important because it's only paid once during data set construction. And then downstream, these models can be used and deployed in a variety of different ways that allow us to have, a much higher fidelity just from the distilling process. Okay, so I guess like now that we've talked about some of these, the deterministic markdown and stuff like that, we just use markdown as the standard target for OCR benchmarks. The reason why is like it's very, very common for these models to just have regular text as the output, and we want to be able to put them into the standard benchmarks in order to make sure everything was correct. And then finally, once we have that, we basically take the input raw image that we had, the really high quality raw image itself, and we basically randomly sample a distribution from dust artifacts, scan lines, blurring, rotation, and these are supposed to actually mimic the real degradation process, not just generic, synthetic perturbations that you typically do in a computer vision task, where you just like augment the data set. These are really critical because they actually do a ton of important distribution mimicking for the actual scanning and faxing processes. So you can take a look here. So in the top row, we have our actual original data set. On the bottom, the second row here, we actually have the HTML representation of the data set I mentioned. And then the final row, you can see the actual rotation scans and the synthetically perturbed faxing processes that we have at the bottom. So you can kind of see the progression of how we're degrading the quality of the inputs in order to mimic the distribution that we would like. Finally, just some regular data set statistics here. We have a really long tail of character lengths in the Markdown, but typically they're between 0 and 5,000 characters seems to be the standard for our data set. So we basically fine-tuned Qwen3 VL on our data set in order to kind of like improve on the processes. There's two main contributions. The first is an interleaved MROPE, and then we also have a DeepSeek visual injection feature injection processes. So why do we use interleaved MROPE? Well, the first thing is that standard multimodal rope processes, they basically allocate contiguous blocks. And the spatial structure can collapse if the band saturates, meaning that like if you have a really large height process, then it like basically collapses down. In interleaved MROPE, they distribute the temporal height and width positional frequencies across all these feature dimensions. So they are more stable with better fine-grained encoding. And this is really important because in our use case, where we're basically rotating the document's inputs and we have different variations on resolution, we want to be able to spread the information across the encoding space more appropriately, as opposed to having a, one axis where it just saturates into. And the second key thing that we looked at architecturally was the deep stack visual feature injection. So in a typical VLM, they would take the final encoding layer, they would project it into the token space, and the LLM sees it as one giant visual stream. But in deep stack or Qwen3 VL, they basically have a VIT that injects them multiple layers in like a residual format. And that kind of allows the spatial grounding without the super bounding box supervision, which is really important because it allows our DLA-free formulation as opposed to having I've been saying DLA here, that means document layout analysis, which is typically a pre-processing step that happens. And we skip that entirely by leveraging these two core functionalities here. Okay, so super quick, R2, 4, and 8B are small model sizes. The reason why is that we want to be able to deploy these either on-prem or in localized environments that are really heavily resource constrained. You can imagine that some of our customers are downstream. They say like, hey, we don't want to have it'd be great to have a 60, 500B whatever model and get really great results, but we just don't have the capacity for that in our system. And so what they typically do is they will have a much smaller model running locally or running in their infrastructure. And this is really important, which is why we only train a small family of models. They have the same native resolution encoder, and they handle dynamic input sizes. These are pretty standard. These are just the regular architectures from Qwen3 VL. And so you can kind of see the per sample structure here, where we had the input vision tokens, the prompt that we had, which is very standard, and then we wanted to target the markdown. And this is very, very standard again. This is next token prediction, very, very standard. But it was basically a full SFT, full fine tune on our data set. So there's no LoRa adaptation or anything like that. We wanted the model to really have that distribution shift embedded into the model itself. Just on some training discussions. We use PyTorch 2.3.1, regular standard, Flash Engine 3. The reason why we use Flash Engine 3, these hopper kernels, is because they have long context, right? So they're able to fit a lot more context for these dense patch tokens, the input visual tokens, plus prompt and all these other information that we need, as opposed to a much shorter, different kind of like prompt. We wanted to have the ability to, I mentioned earlier, the context length was 8,000, the most of the variations within 0 and 5,000 character tokens. Um, so having a context length of 8,000 was basically where we felt it was appropriate. The real thing is that all of these three model sizes can be trained on a single H100 in under 2 hours. And that's a key aspect here, right? We want to be able to use this data and use these models downstream for our customers and be able to fine tune for them downstream as well. Cool. Now the exciting part, some evals. Typically, the evaluation metrics used in this process is something called average normalized Levitch similarity. The TLDR here is basically that it's a distance between two strings and looking at the difference between them. And so we just average that across the entire data set for our raw and our actual results coming out. So the really headline result here, this table is the headline result. The first thing is that in all three model classes, in the small model class 1 to 2B, we still outperform the other model architectures. So SynthForm outperforms Paddle OCR. Paddle OCR is one of the best OCR models online right now, and it beats benchmarks despite only being 900 million parameters. And we have a significant improvement over the Paddle OCR there. Um, Same thing in the 3-4B class. We have a 9.3 result, not 9.3% result on the ANLS. And again, these are all relative to the Qwen3 VL AP baseline, which is incredibly impressive given the fact that SynthForm-VL 2B is a 2B model, which basically has a 6%, approximately 6% increase, right, compared to a AP baseline. So basically, a different way of framing that is a model, a fourth the size of the baseline is still has a 6% improvement, which is incredible. And this is really because, again, the distribution input shift is the real bottleneck for all of these models. Yeah, so this is kind of what I was just referring to earlier, where we have just gigantic wins across healthcare, dental, SEC, where the ANLS is absolutely massive, the delta in the ANLS is massive. And I mentioned earlier, like our 2B model outperforms the unfine-tuned AP baseline. So the pre-training corpus just does not have these perturbed forms, and it is not reasonable to assume that these you can just take an off-the-shelf OCR model for any tasks. And some of the other gains are smaller, as in this 2B insurance task. It's typically because we just had class imbalance there. So we could have definitely improved on the process. Yeah, so you can see the Pareto frontier of what we've evolved here. The cost per million pages. We outperform a ton of different models here. The Reducto, almost CR, almost CR2, and a bunch of these other model architectures that you can see. And at a relatively reasonable cost, we get massive gains in the output performance here. So on the H100 that we have, we're running this at very reasonable cost relative to the actual other baselines here. So it's very competitive in terms of cost regarding the other processes. And we basically have effectively used the high reasoning agentic mode from GPT-5 in order to generate a higher quality of data for our output results. Cool. So why does this process actually make sense? The first thing is the out of distribution input space. I mentioned this earlier, but it's basically all of the OCR models online right now have been, trained from millions of clean documentations from archive, from these forums online, from scientific literature, all these other places, and they're all clean document images. But none of them are actually representative of real world challenges that we face, like faxing, scanning, the actual stuff that we see in a regular process. The second thing here is that these targeted perturbations are much better than the generic augmentation that you might do. So in generic augmentations, you would just, rotate, crop, do the standard practices, but they don't actually effectively perform well because they don't actually represent the input distribution they would typically use. The third interesting thing here is that these smaller models have really great capacity. So the pre-training capacity is unlocked, not added to, meaning that we are basically, even though they've been pre-trained, we have the ability to like do really well in these processes. So targeted SFT is the like Pareto better option for scaling this task specifically. And the 4B is the capacity optimized sweet spot. So what I mean by this is that the bottleneck typically is this compression under these noisy inputs. The 2B has the topology, but the mapping is like not really great. You saw that the results were 66%, while 8B has a great capacity, but the jump between 4 and 8B is still a 2x jump, but the relative value is only 0.9% as we see here, meaning that the 4B has the greatest capacity optimized value where we can actually deploy the 4B model to our customers and they can say like, okay, we're getting the maximum bang for our compute basically. Just taking a more broader step back. In ANLS, there's a part of ANLS where the tau value is zeroed out under a certain tau value. And so we find this to be a really big bottleneck on the metric itself, because as you can imagine in forms, they're very short fields where a one character error in a five character field is like a 20% deduction. And so we have to generate a new process here is our thinking. There are also some other like, Paddle OCR has 0% on insurance forms. And this is just because there's extra prefix tokens that Paddle OCR deploys. Yeah, so ultimately we think that ANLS is a interesting metric, but the field broadly has to take a closer look at ANLS as a reliable metric for OCR and VLM document processing because it's not quite as good of a metric as we originally thought. Um, some of the open challenges that we face. Number one, the reading order is ambiguous. In DLA processes, the document layout will basically give you the document layout first, and then you process it all at once. While in our case, we read the entire page all at the same time. So that means there's no reading order signal in the SFT data. When you read a page, you like scan down, and you get better understanding there. But typically, in this case, it doesn't seem to be the value is not there. Another thing is our data set was highly imbalanced for specific categories. For example, insurance, we only had these 68 samples. That's because I had to go and hand sample them, while in larger scraping, we got the CRA data at 800 samples. So there's a big gap here that we need to augment some of our low resource domains. Yeah, and we did see some exposure biases during the HTML generation, but there's some tail tokens that were really malformed at the dense forms. But ultimately, we still found that the results were reasonable, but it's something we should take a closer look at in the future. Yeah, so there's some interesting directions here. I think on the data set, we can improve it earlier, as I mentioned. The modeling, there's an interesting paper out of AI2 where they do RL on visual unit test rewards, which is where we can use the HTML. So definitely interesting stuff there. On evals, like we have this field level F1, which I think could be the better metric as opposed to the ANLS directly. Cool. So just as a final conclusion here, the takeaways, the data set and the model family. The data set has 3,400 perturbed samples from forms. The model family is a full parameter SFT where we do really great improvements that we're seeing in this Pareto frontier. And the ultimate like vision as we're talking about this is like when you are training these models, you really have to think about the pre-training mix. What has this model been trained on? And whether if you're just doing this in scientific literature that is in distribution, maybe a off-the-shelf model can work. But in these cases where you're looking at long tails, it's really important to do fine-tuning because the input distribution may be completely off the charts and you have to really take a closer look at the data that you're analyzing. Yep. And yeah, thank you so much, everyone. Really appreciate the time today to talk to you all about our project. And thank you so much to Eagle as well, our co-author on this project.